thank you to everyone who's joining online over Zoom. We long for the day when we can all be back in person in one spot. So welcome everyone. My name is Paul Novertil. I'm one of the paper co-chairs for LDAV this year. And we have a very exciting program for you today. And I'm really thrilled that everyone's here to partake in it, and really honored to be here as part of the esteemed colleagues that helped put on this symposium. It's really in for some good content today. Just a short review. If some of you are new to the LDAV symposium, we have 4 goals. First is to meet, to just bring us together, particularly folks who are dealing with big data. And of course, there's always the perennial question, what is big data? And I like to think of it as anything that your laptop can't do is starting to get into big data contexts. And we can have conversations and debates about that over various beverages throughout the week. But basically, this is where you really need some advanced computing to help you solve your analysis problem. And then talk, basically getting that information exchange together and allowing us to lay a course for the research goals and the service goals for this community and for the broader Viz community, frankly, into the next years for both us and the next generation. Because the big data problems of today become the normal data problems of tomorrow. So we have this venue to highlight work and to publish best practices so that we can all improve our capabilities, and to learn, to understand how things work, understand how other ideas might apply to our own research goals, and to just basically lift everyone up into a more productive, more fruitful analysis process. So this is the 12th LDAV, and we have a history of being associated with Viz for our entire 12 years, and so we really enjoy that. And again, this is a hybrid. I think it's the first hybrid version. Last year was all online. So again, thank you for being here in person, and if you couldn't be here in person, thank you for joining the Zoom. We really appreciate the service of our steering committee, Jadine Bennett, Hank Childs, Christophe Garth, Ken Moreland, Julian Tierney, and Hongfeng Yu. Their experience and guidance in this domain and their considerable experience in large data analysis and visualization overall is really invaluable. And thank you to our general chairs, Timo Bremer, Christy Potter, and Chao-Li Wang for being our shield interacting with the rest of IEEE and with the Viz conference to make sure that we have our spot and that we are able to put this on today. And thank you to my co-chairs, Joanna Beyer and Stefan Frey. I guess I drew the short straw to be up here, but I appreciate y'all's work as well. I'm really proud of what we were able to put out this year. And thank, of course, to the poster chairs as well. Jonas Lukasik, Silvio Rizzi, and Stefan Zellman. We really appreciate the posters showing new ideas and concepts that are up and coming that we hope will be full papers in upcoming LDAVs. And of course, many thanks to all of the folks at Viz and at IEEE that helped us make this process to get to where we are today. There's just a lot going on behind the scenes. If you have never been part of a conference organizing or a symposium organizing, it's a very eye-opening experience. I encourage you to volunteer and become part of helping our community have events like this. So a bit about the technical paper review. We had abstracts due in middle of June. You had to submit an abstract in order to get the paper. That just helps us sort our review committee into the various which papers they may want to review. And then the papers were due at the end of June and had about a month for the review. Single blind review, you don't know the reviewers, but the reviewers know who the paper was from. And 3 program committee members assigned per review, 1 coordinator and 2 committee members. And then there was an online discussion phase after the reviews came in order to reach consensus. And we had 32 members of the International Program Committee, well represented both geography and in terms of discipline and pursuit in academia, industry, and across U.S. national labs. And they're listed here. Thank you again for your service. We literally couldn't put this on without your time commitment in order to give quality reviews to the papers. For acceptance, we had 17 abstracts and 14 complete submissions. Sometimes the abstract is more of a hopeful submission and doesn't always come into a paper. And then from those 14, we had 6 manuscripts accepted, which is about 43%, which is in line with previous years' acceptance rates. We had a best paper review of the highest scoring papers. Performed a separate review by a best paper committee, and the paper selected as best paper will be published directly as in IEEE TVCG. The remaining papers are published to IEEE Explore and part of the proceedings. And with that, I would like to invite up Chao Li to introduce our keynote speaker.
Okay, thanks, Paul. And so I'm very glad on behalf of the Timo and Christy of the symposium co-chair to invite Professor Han Wei Shen to give the keynote. So Professor Shen is a full professor at the Ohio State University. He's a member of the IEEE Academy, and he's the associate editor-in-chief of IEEE TVCG, and he will be the incoming editor-in-chief of TVCG in January 2023. His research mainly in scientific visualization and computer graphics. Professor Shen is a winner of the NSF Career Award and also DOE Early Career Investigator Award. He has published more than 50 papers at IEEE Viz and IEEE TVCG. So with that, we are extremely happy to have Professor Shen to give our keynote.
All right, thank you so much, Charlie, for the introduction. So it's my great honor to be here to present some of our recent work on using machine learning for scientific data analysis and visualization. So as we know, AI have been, in particular machine learning, neural network has been applied to many areas. Just like other disciplines in the scientific data analysis community, we have seen a lot of papers in the past 4 or 5 years various things, for example, visualization surrogates for analyzing simulations, doing embedding, and also we have seen a lot of super resolution papers, data reduction, and we have seen that using neural network for one rendering, and obviously for classification, because that's how most people in computer vision community are used for. And finally, we have seen papers that start using the intelligence in the machine learning for visualization layout and the design, etc. So now, since 2017, my students, I think it was like one of my students went to industry for intern, and he brought back this new concept of, hey, we need to use AI for a lot of things. And then we start to experiment. So we have done some work in the past 4 or 5 years, but today, because of time, I'm going to focus on 2 things. One is our effort in developing visualization surrogates, because it kind of has a particular challenges and also will bring potential a lot of benefit to scientific computing community. And also, I'm going to talk about embedding, like how do we represent data using latent representation created by autoencoders. So I'm going to start from the ensemble simulation analysis first. So let's look at a typical ensemble data analysis workflow. So basically, scientists, they want to, in order to run a range of the parameters such that they know the possible outcome from simulations, typically their simulation will take input parameters. right, to control the boundary condition, the initial condition to control the output. But what they do is actually, they are not quite sure what parameter to use in order to generate phenomena that is most closer to the nature phenomena. So they need to run a sequence of simulations. And that, as you know, those simulations will take time. Not only that, they're actually going to generate data, a lot of data. Each set created from one particular ensemble run. Now, when we look at this data from the post-hoc, not only the simulation itself takes time because we need to run many, many instances of it. Obviously, the data is a problem, which is why we have this conference. Now, to solve this problem, in the, I would say, past 10 years, people have been doing something we call that in situ visualization. So what is in situ visualization? Instead of saving the data to disk, right? Why don't we actually produce visualization on the spot where and when the simulation is running, right? So now we actually replace the storage of the 3D data by a pre-selected visualization algorithms. And also, inevitably, we need to pre-select some viewing parameters, transfer function, and etc. because the output of the in situ processing are images. Now, comparing to storing the data in 3D, as you can see that image data are 2D and they are much more succinct, right? I guess people in the in situ processing community, people try to see what are going to run and also how are we going to analyzing and utilizing the 2D images produced and stored in the disk, right? For example, by interpolating of the views such that they are able to see the same data, but from different view in the post-hoc analysis process. There are many, many packages. For example, probably we all know that ParaView and Catalyst, they have a pretty good support in terms of visualization. But is that the end of it, right? So one thing the reason we going forward for helping in situ analysis is that it still takes too much time to run the simulation alone, right? Because like I said, you have to try out a sequence of possible parameters in order to simulate something closer to what we observe in nature. And that alone, without thinking about storing data, will take a lot of time. Second, a lot of time we don't even know where to start. Like I work with a biologist in the lab. They say they have a system of partial differential equations. There are 35 parameters. And in the meantime, they collaborate with biologists in the lab. They have a specific scenario they want to simulate. But when they come back to mathematics department, my collaborator, they don't even know what parameter to use in order to produce the phenomena similar to what the lab produced. So to handle these challenges, we can see that obviously it's not sufficient to just produce images and output because we're not able to really allow the scientists to experiment parameters. Now, the solution we're trying to come up with is that can we do something like a visualization surrogate? So what is visualization surrogate? That is, we actually bypass the simulation completely, produce a system that is going to quickly produce images. The scientists only need to input the simulation parameters, then the output is the images. We entirely do not need to store the data. And that's the idea with simulation surrogates. Now, the simulation surrogate, which the output is the images, and our idea is that we want to not totally forget about people have been trying in the past decades in situ processing. We actually want to incorporate the result produced by in situ processing software and use that to produce our visualization surrogate. And optimally, this is actually something we're still trying is we are trying to say once we generate a surrogate, we're actually going to allow the scientists to experiment, to test without needing to spend a lot of time in the simulation. They are able to, by looking at the result, they can see this parameter is going to allow me to produce a result closer to what people observe in the lab. And that's our ultimate goal. So in 2019, my research team developed something called in situ net. So that is actually to produce a visualization surrogate. So we want to know that our goal is not to replace simulation. We're not trying to replace the simulation and generate the data directly, but we want to allow the scientists to obtain a quick preview of their simulation run without even running the simulation. That's one goal. So now, as we know, the image is essentially a function of the following parameters. The simulation parameters, the visualization parameter, which is the algorithm, and ISO value, for example, and plus a viewing parameter, which direction you want to look at data in a, say, viewing globe, right? And then because visualization images is essentially a function, why don't we replace the actual simulation plus visualization by a neural network to model this function, right? So the way we do this is we're taking a lot of images generated by in situ software. We actually record the specific parameters associated with that images, and then we use a neural network to train. So let me give you a slide description about the neural network. So essentially, it's a deep neural network that we have 3 subnets and 2 lossless functions. So regressor and feature comparator and also discriminator. So now essentially you can see that the regressor is to produce images and based on the parameter we learn from input to output. And then how do we know the images we produce is close to what usually were produced by simulation and the visualization algorithm? Now, of course, we have ground truth. Ground truth images are collected by in situ processing programs, right? So we want to make sure that the image contain all the necessary essential feature. So we actually basically use a subnetwork based on the VGG19, the very popular computer vision network, to extract low-level features such as edges, such as lighting, stuff like that, from the VGG19, and then we feed the same. Using the same neural network, we use the ground truth image to extract features. And then we compare the features between the ground truth feature extracted by computer vision component, VGG19, and also the feature we generate by our regressor. Now, this is one loss function. The other thing is we also use a generative adversarial network gain-based discriminator. Essentially, we want to train the neural network such that the discriminator will say, no, this is not a real images. Or yes, this is real images. The reason we do that is to avoid the comparator or basically the MSE-based error will tend to minimize the error but blur the entire image. So we want to use a gain component to add some necessary detail such that we are able to highlight and model those high frequency features. So altogether, basically the convolutional-based neural network take a feature loss and also a adversarial loss, and we feedback. And this is, if you have worked on neural network model, you know, we're just basically using backpropagation. And just to be a little bit more specific, in the regressor we have is a combination of a multi-layer perceptron, fully connected neural network, plus a skip connection, the ResNet, together to perform the most important regression task. So this is just want to show some kind of animation here. This, if you zoom in, hopefully you can see that. So essentially, this is a interface we produce for in situ net. Essentially, the user is able to change the parameter, viewing parameter, and then also the top 3 rows are the simulation parameters. Now, the line graph you see are the sensitivity of the result to the input parameters. Now, let me play this again. So now we are changing the viewing parameter. This is entirely produced by neural network. There's no data involved. And then the user can go up to simulation parameter so you can see the feature has changed. And this is essentially what we, based on the trained neural network to generate the simulation result and the images. Now we also offer some capability of sensitivity analysis. Now, if you see the image patches somewhere, like here, you can see it, that will tell you this region of the image tile is most sensitive to the given parameter. So now the scientist is able to look at the sensitivity and then can see this parameter, maybe I need to tweak a little bit. Now, again, what do they do out of that? What is the actionable thing to do? They will collect a bunch of parameters such that they are going to use those parameters to run the real simulation to do a further analysis. And this is actually our visualization surrogate's main purpose, not to replace, but to allow them to do a quick preview. And this is actually another result we run on Impact Ocean simulation. Again, the bottom slider are the view. You can change the view, and then the top is one parameter we allow the user to modify, and they can see the change of isosurface and from the simulation on the fly. So this is what we have done for 2019, and actually won a best paper award in 2019 conference, Science conference. Now, after that, we continued to push the technology for the past 3 years. So then what are the limitations for InSituNet? First of all, it only produces 2D images. It doesn't produce data, right? Because our goal is to produce a visualization surrogate. And second, the images are generated from a fixed set of pre-selected visualization algorithms. For example, if the images are produced by isosurface algorithm, then you can only do isosurface of different value. You cannot change it to volume rendering. If you want to draw isocontour, you want to do a slicing, you cannot do that because those are not in the training data. And finally, another limitation is because it's convolutional-based neural network, they can only process structured grid data. Now, how do we overcome? So I'm going to talk about the first thing, overcome. We want to kind of take a one step further to generate data as per the images. So we want to extend 2D to 3D. So this is a natural path. But again, we need to keep in mind that our motivation is not to replace simulation. So what do we do? And also keep the computational cost in check when we extend to 3D. So let me present our idea here. So now what is the challenges here, right? If we extend our InSituNet to 2D to 3D, InSituNet was already pretty complicated for generating 2D images. If we want to push it 3D, first of all, it's going to become even more expensive to collect training data because the training data is going to be 3D data, all right? And then that will incur inevitably larger storage cost. Second, well, from 2D images to 3D data we train, it will take a lot longer training time. And the network become much more complex, right? And also it will require, from 2D to 3D, it will require a larger GPU memory because now people use GPU to train neural network mostly. And then the GPU memory are expensive still and a limited size. And also, if we extend from 2D to 3D, then we have to ask ourselves, are we taking advantage of in-situ processing or are we staying away from it? And we are doing the same thing like what people try to do in a lot of part of our component. So how do we incorporate the in-situ visualization processing output is also something we were thinking. Now, those are the challenges. What are the strategies? So first of all, in order to keep the computation cost down, we kind of remember ray tracing. Right, where you have a lot of data, like a 3K by 3K by 3K, but if you actually do ray tracing, generate image of 512 square, for example, you really shouldn't, take all the data, like you cast a ray. So this is actually when the case that ray tracing become more popular because you can cast rays through the scene. Say you pre-select a resolution, you cast rays, so then you swap from the data space complexity to image space complexity. So here we are trying to do the same thing. So in the InSituNet, basically, we are now actually trying to predict the full resolution 3D data. We will pre-select a visualization resolution for the images, and we actually only predict the data along the viewing rate from every pixel. This way, we are able to provide the highest possible visualization quality for the image resolution that we chose as appropriate. That's one thing. The second strategy is that we still need to collect samples along each pixel, and then those samples are still costly in terms of the both computational complexity to process and also storage. So we decided to use autoencoder to actually collect the data, train a latent representation, and then our surrogate is actually predicted latent and also train the latent. And after we obtain latent for a given visualization parameter, then we use autodecoder, the decoder part of autoencoder to recount the data. So let me give you a little bit more specific. So given that this is 3D data, then we chose a proper visualization resolution. Like for example, we don't need to look at 3K by 3K square images. We only chose a smaller resolution. And then for every ray we cast from every pixel, we'll collect data samples. Now, those samples are something we are trying to predict and reconstruct at the end of the day. But we are not trying to process the raw data directly. We actually train an autoencoder. The sample is going to go through the autoencoder and then generate a latent representation for each sample ray from the pixels. And this is what we call a ray-based autoencoder. Now, what is this used for? Once we have the train-based autoencoder given a simulation data, we actually, in the in-situ time, we do raycasting, just like what people always do for violin rendering. We collect the samples, and then we feed the sample into our ray-based autoencoder and generate latent. And then we have a bunch of latent variables represent the data along the depth for each pixel. Then we actually start to develop our surrogate. Our surrogate will take a simulation parameter into account, which we use very similar architecture as what we use for in-situ net. But now we are training on the ray-based latent representation, and also we predict the ray-based representation. Now then, the training is as usual, we compare the losses between the predictor latents for every pixel and also the training latent collected from our in-situ processing. Now, once the network has trained, then we could, for a novel parameters, we go through our surrogate, which is a view-dependent latent predictor, and we produce a ray latent for every pixel as the predicted simulation output. Then we use that, our pre-trained decoder, to decode and reconstruct the three-dimensional data. Now, one thing to note is that because we are taking a view-dependent approach to train the view-dependent ray latent, and then you might wonder, then what view do you choose? So basically, we choose three orthogonal view and to pre-train our surrogate predictor. If you want to look at the data from an arbitrary view, what you can do is you can actually, predict the result from three orthogonal direction and doing a warping and the view interpolation. And then that result is going to be the best view along the ray for the data for a given selected view B. Now let me show you some example quick. So this is actually a comparison. The animation on the left is the ground truth data to produce a 360-degree animation. And the image on the very right were something produced by our in-situ net, which is image-based approach. So we actually predict the images frame by frame. As you can see, there's a lot of like an artifact and a popping effect, right? This is a typical thing when you do violin rendering spatial algorithm without considering the coherence of the view. But now our VDL surrogate, we actually, because we predict the 3D sample along the view ray, and actually we do a warping and interpolation of the 3D orthogonal view, and we have 3D data to process and to do rendering. So we are able to produce something a lot better quality compared to in-situ net. And this is another example. The leftmost animation is produced by the ground truth data. This is Empire Ocean simulation. And then the very left is the in-situ net. You can see kind of an artifact, but the image in the middle is something we produce from we call VDL predictor, our view-dependent latent surrogates. So this is how we overcome from 2D to 3D. What else? In-situ net and also VDL predictor surrogate are all based on convolutional neural networks. And as we know that convolutional neural network require structured grid data. Right? And now for a lot of simulations, now they're using unstructured grid. For example, the Empire Ocean data we try is actually unstructured grid. What do we do with it? So now then we decide to move one step further. Can we create visualization surrogate for unstructured grid data? Now the answer is, why don't we explore graph neural networks, GNN? So the idea is the following. So let me give you a very quick overview. So GNN is another way to perform convolution on graphs. Essentially, every node is an entity. Then we are going to perform some kind of message passing, which is a weighted sum of a property from the neighboring node if there's a direct connections. Now, to start with the training and also prediction, initially you need to assign some sort of a representation. We call a latent representation for every node. That representation is related to the property you are trying to simulate, such as temperature, pressure, density, or the scientific simulation. So now initially we have that. And then in the message passing stage, going through multiple layers, every layer the node is going to collect information from the neighboring node to perform weighted sum, which indeed is a convolution. Now, going through multiple layers, we are able to capture low-level detail to high-level detail. Then essentially, and we call it going through this linear transformation, nonlinear function mapping, and we train iteratively. Eventually, we are able to predict the output. So now let me give you some kind of motivation for our GNN work. So essentially, like I say, we want to model unstructured grid mesh. So impact ocean is actually a unstructured grid. Horizontally, which is on the surface of the Earth, there's a hexagonal cells, which is a result of Voronoi tessellation. And as you can see, they are not structured grid, rectilinear grid. Then vertically, basically we are using the same kind of cell structure, but we scale and then condense and we connect to adjacent layer to form a vertical direction mesh. So it's a three-dimensional unstructured mesh. Now, what we do is actually we convert basically the connectivity between nodes into a graph where each node is a center of Voronoi cell. Then all the property we're trying to predict are predicted on the center of each Voronoi cell. And the edge of the grid of the mesh of the graph is actually a connectivity between adjacent cells. This becomes a graph input, and we are going to use this graph representation for this unstructured grid to train our GNN, graph neural network. Now, of course, I'm not able to present too much detail, but one of the key components in our training is we need to keep the cost down. When you have a unstructured grid, you can easily have a lot of nodes and also a lot of cells. So then, for that, in order to keep the computation cost in check, and also in order to model low-level detail and the high-level detail, we need to perform graph coarsening. So essentially, basically, we are going to do an edge collapsing. So for neighboring node, which is coming from our mesh, we compare whether the value deviate from each other too much. If they are homogeneous, we collapse the edges. So edge collapse is actually a key part of the graph neural network in order to keep the cost in check and also in order to capture local to global phenomena. So from here, this example, we collapse edges comparing the simulation output that interests the scientists. If they are very similar among different ensemble members, we collapse. Now we create G0, G1, G2, and so on and so forth. And each of the graph is going to be mapped to one layer of our GNN. As you know, when you do GNN, you have downsampling, upsampling. How are you going to downsample, upsample? We're based on this preprocessed connectivity that using adaptive mesh resolution. Now, once the graph has been prepared, then we can feed that into our GNN for training. And the input of the GNN is the simulation parameter, just like similar to in SequenceNet or VDL predictor. The input is simulation parameters, and the output are the simulation result on the impact ocean grid, for example, in a adaptive resolution manner. And also, I want to know that we actually not directly model the simulation value. Because remember, we are trying to do surrogate for ensemble. We pick one particular round as a reference, and then we compute the difference of other ensemble round to that particular reference as a residual. And then our GNN is actually to train and predict the residual as opposed to the actual simulation result. All right, so now very quick, so you can go to our paper. So in the end, I'll tell you where to find the paper about the data. So now this is the impact ocean simulation for a given set of parameters. Now what we do is actually over here is from top to the bottom, and left to right is ground truth, and then GNN surrogate, which is our product, and the bottom is IDW interpolation. That's one particular interpolation scheme, and also in SequenceNet. And then please pay attention to local region in the red rectangle, and also I highlight this difference images because I want to show you the accuracy. Now, as you can see that if you look at the bottom, there's a lot of difference for the images, the data visualization, I want to say, predicted between the interpolation scheme, the SequenceNet, and the ground truth. But if you focus on the upper right, you can find out the difference is actually very small, i.e. actually using graph neural network and also adaptive meshes allow us to keep our training costs in check and also produce high quality images. So this is about the GNN surrogate. So let me kind of switch gear a little bit. But let me summarize. So from 2019, we actually create a series of visualization surrogate. And then from a image-based to data-based, but we keep the resolution refined constraint to image resolution, and then we extend our surrogate to GNN so that we can handle graph neural networks. What else do we do? Now, one thing I hope you remember in the VDL predictor, I mentioned the use of latent. Latent is actually something that produced by autoencoder and which has been used a lot by different computer vision or data analysis application. Essentially, autoencoder is a unsupervised machine learning component which will take the input of raw data and going through information bottleneck and then produce the most succinct representation but information-rich representation for the input data. We call that latent representation. And then actually, because we use that, we're able to press down the computation cost for our VDL predictor. But what else can we do, or what else we need to do? Now, first of all, in the science community, people have been using the latent representation, doing a lot of really great work, for similarity analysis, because you can compare the difference between latent and to focus on more interesting feature, because latent is a succinct representation. And for simulation synthesis, this is similar to our VDL predictor. Instead of a simulate based on the raw data or predict raw data, we actually simulate based on the latent and predict the latent. And because the latent, we are confident that it can be reconstructed back to raw data. And also, finally, for data reduction, because latent has similar size. Now, what's the constraint? Now, for most of the autoencoder, when they produce latent representation, there's no differentiation about data importance. Like, suppose you divide the data into blocks, all the data blocks are considered equally important, and they are going to be used to produce latent. This inevitably, first of all, is kind of a wasting space if the scientists are not interested in all the regions, all the data, right? Second, the latent representation may contain, because it's unsupervised, it may contain too much information that you don't want. So it will be much nicer and desired for us to actually incorporate importance into the latent generation. That is, if I have a preset idea what is more important in my data, like any value below something I don't really care, so the surrogate doesn't need to spend too much effort to predict those regions. Well, it would be nicer if we can incorporate importance into our latent generation. And so this, not only that we're able to further reduce the size, we are able to allow the scientist to focus on only the important thing in the latent, only the important difference, not the unimportant difference to misguide the decision. But important, this is actually something that people have not done mostly. You could probably force to do some kind of training, but one very important goal is we don't want to retrain the model every time you change the definition of importance and wait for hours, right? That's something we want to avoid. So now let me present our idea. So to incorporate scientific knowledge or importance, right? What we do is we actually add one additional component to our autoencoder. That is something I put here as importance. The importance is going to be input together with the raw data, and our encoder is going to be modified such that the output of this latent is important-driven latent representation, which actually only focus on important portion of data. You can consider as data value. You can consider as a data value, you can consider as spatial location, you can consider as a feature, anything you name it, we want to inject that importance into our autoencoder and capture that. So now our method, let me give a quick overview of our method. Our method can be divided into 3 pieces. One is, first of all, what is important? How can autoencoder recognize it without being too specific for any particular type of importance? So what we do is actually we create something we call importance map. Importance map is a spatial map which has same resolution as your data. For every voxel in the data, we actually record a floating point value. High value means more important, low value means less important. For example, suppose you take an isosurface example, you are actually focused on one particular value, then only a voxel in the isosurface has high importance. And that is being converted from the data into something we call importance map. All right? Now, this is the importance map that we use. Second, we are going to inject to the importance. How are we going to use that? Essentially, we need to add some additional subnetwork. The subnetwork is going to consider the raw data value as well as the importance map and then guide the generation. So you probably know that all the latent representation is created from something called feature map in the model. So now we are going to use the important map to alter the feature map to translate, scale, and shift so that the feature map is going to be altered. So only the important region will have a high fidelity, but unimportant region we are going to compress it, suppress it. So this is something my students are going to present this week, but basically we are using something called spatial feature transformation layers that will take the importance map and then raw data as input. And actually, I would say a feature map produced by the ODE encoder as input, and it will perform scaling and translating such that we are going to alter the feature map and send back to the ODE encoder to encode the data properly by taking into account the importance to generate the latent representation. Now, so what is the consequence of this? Consequence is that after we have this transformation, data in the unimportant region, their value is going to be suppressed. And data in the important region, their value is going to be stretched. Now, even suppressing stretch, they're not going to change the length of latent yet. So what we need to do is we need to add another component to do quantization and also compression. So what we do is, this is a traditional, like a ODE encoder enhanced by our importance map. And then we are going to actually taking the raw latent Y here, we're going to send through quantizer, because as I say, unimportant data being suppressed, right? So once quantized, they are going to take a fewer numbers of variation in the range, but then we stretch the important region, the quantizer is able to differentiate the difference by more bins, right? The quantizer is going to be sent through entropy encoding so that we are able to do a lossless encoding of the quantized latent. Eventually, we're trying to decode that's going to produce output as the raw data. So essentially, so the difference here, we actually use a additional network to emphasize and change the feature map and then perform quantization and compression such that we're able to throw away unimportant features. So this is just a quick overview. So now, like I say, we promise that we don't need to retrain the model when you change the important definition. So here, the 3 rows are 3 different importance, which is the log density of the next simulation output, which is a cosmology simulation. So the first row is greater than 9.9, the second row greater than 10.2, the third row greater than 10.5. And then we evaluate based on the size, compression rate, and also the quality. But now let's just focus on the middle part. So the baseline is a vanilla autoencoder, doesn't incorporate importance. Now the first column, the PSNR is 30, which is produced by our important-driven autoencoder. The second column is the PSNR produced by the vanilla autoencoder. So between 30 and 31, you can see that the quality is similar, which means we preserve the important portion of the data. But now if you focus on the compression rate, the data size, right? So we are able to compress data to more than 200 times, but the vanilla autoencoder is only able to reduce data by 7 times. So this means that not only we are able to preserve the quality deemed important by the scientists, we are also able to reduce the size by a lot. And an add-on benefit is we throw away unimportant things. So when you do a similarity comparison, it will be much more informative. So let me finally switch gear. So this is the autoencoder, how to incorporate importance. So far, all the autoencoder I mentioned, they are based on convolutional neural network. But for particle data, there's no connectivity, right? So how do we perform convolution, right? They are not even graphs. Then some people may say, hey, why don't we just convert the data into regular grid and do latent extraction? But this is very susceptible to errors, right? So can we do something much more native and differently? So what we do here is we actually develop a particle data-based autoencoder to capture the feature around every particle, because every particle we can define given a radius, we can define a particle patch. And then for all the particle within the particle patch, we actually decompose the attribute and the position into several orthogonal components, and then we use autoencoder to compress that decomposed and decorrelated feature into a succinct representation for particle, focus on describing the local structure of the data. So let me give you a little more detail here. So our method has 3 parts. One is, like I said, I want to decorrelate the data information of the surrounding particle into orthogonal direction. So first thing we do is directional features, and then we decompose the direction feature, then we actually For every particle, we represent the particle in the patch by their decorrelated features, and then we combine. So this is too much detail, but essentially maybe visualization will help. This particle P is the center, and the particle Q is one of the neighbors, right? For each neighbor, we take the attribute, we project to X direction, Y directions, right? And then this essentially we decorrelate the feature into 2 orthogonal directions. Now, for each direction, we sum it up to indicate the influence of Q to P in different directions. They are going to be represented in different number in a latent vector. Now, for each particle, given a path, there are many particles, like a red particle here. Then we do a weighted sum of decorrelated features from each individual particle. Eventually, we create a descriptor. This descriptor describes the geometric information, which is position, and also attribute component, which is the value you are interested in. Then we use an autoencoder to suppress and convert the information from a feature descriptor for particle patches through the information bottleneck. And then the encoder is basically this is called geocount. Geocount is a building block we use to extract local features, and we use that local feature, imagine they are feature map by the autoencoder to generate latent representation. And then when you want to use the particle, you can actually take the latent to the decoder, and decoder is able to reconstruct the position of the particle in the patch as well as the value of the particle in the patch. All right, so this is actually how we overcome that particles are meshless, and we're able to capture both the position and the attribute information into latent representation. So you might ask, what do we use this for? Well, you can use that for earlier, like a feedback to our surrogate for training particle simulation. Yeah, this is our ongoing work with variations. But you can also use that for exploration. For example, here's just a very quick example. After you have latent, which is a low dimensional representation of particles, all right, you can actually, the image on the left, we do a hierarchical clustering, and we show the tree structure that captures similarity with the particle in the spatial domain. And the scientists can actually go to click on different nodes in the tree and see the projected t-SNE projection of the particle latent on the right. But we have another window. You can connect the particle. You can circle any region. You can see where they are in the spatial domain. Essentially, this will become a much manageable viewing space, because imagine the original particle data may have millions of particles. Each particle may have many dimensions. But now we're able to use the geocount plus autoencoder to reduce the data to something they are visualizable, they are able to explore, right? But eventually, we're going to hopefully to feed this latent representation to our visualization surrogate so we can predict simulation result. And this is the example of tracking. So now latent can be used for tracking because we throw away unimportant information. We actually reduce the high dimensional attribute into a low dimension. So in this example, the image on the left, we are running using a mean shift algorithm to take advantage of particle latent, right? Not the raw data particles. And then we track based on the histogram variation. If you know the mean shift algorithm, we're going to track an initial group of particles circled by the scientists. We can track it. The image on the right, we are using pure attribute and running the same mean shift algorithm. The feature is in the blue box, and you can see that when we look at the animation on the right, we quickly lost track of the features because the number attribute, the dimension is too high for us to keep up the computation. But once we reduce the representation down to a manageable size in latent, we are able to run this same old algorithm mean shift to track the feature much more effectively. All right, so actually this pretty much summarizes what we have done in the past 3-4 years. Now this a lot whole I could not present. For example, this week, you are going to see a paper, how we use reinforcement learning for parallel particle tracing. Our focus is on low balancing, all right? So there's a different aging, we exchange the particles such that we're able to make sure that we work donate to people who don't have work and so on and so forth. And also we have a paper on how do we do super resolution for time varying vector field. And finally, we have a paper on how to use GNN for graph drawing. Those are the 3 papers will appear this week, but I'm not able to summarize. And the following 3 are the paper I just described. The incision net, which was earlier, not this year, but we have this VDL. My student is going to present it, give you more detail if you're intrigued. And also the ILAT, important driven latent representation, my student is going to present on Thursday. And then we have a particle-based local representation also happening this week. And then the GNN work was presented in Pacific Viz this year. This basically we call GNN surrogate. If you're interested, you can look at, this is one of the 4 papers that invite to TVCG. So it's actually appear in TVCG for our GNN surrogate work. So conclusion. So basically, I think what we have been doing is only the beginning. There's a whole lot more work, and I believe that machine learning is going to play an increasingly more important role in scientific data analysis and visualization. And we are going to expect that it will change the way we perform data reduction, transformation, video tracking, classification, simulation, and visualization. Right? It will fundamentally change because we have a new data representation. We have a new way to extract information. And also, the cost is still the key. I think that's still the bottleneck. That is taking too much to train, and use a lot of GPU memory. So the research effort, one of the major research should be put on reduce the cost, which is, I believe, is the focus of this conference. And finally, XAI, right? Because there's still a lot of uncertainty, a lot of unknown. The model is not always stable, so people need to put more effort in understanding the model, which is under the theme of XAI, and in particular because scientific data analysis, which is my focus, is for science, right? So XAI not just for science, it's XAI should be for science. This should be also the focus of the research. Well, this work is done by my student. So, for example, Wenbin was the person create InSituNet in 2019. And then sitting there is a student creating the GNN surrogate and also V-dependent surrogate. Jingyi was student creating the important-driven latent representation. Hao is here. He's a student doing this particle-based latent representation. And Jia is going to present reinforcement learning for particle tracing. And finally, Xiaoqi, she is going to talk about GNN for graph join. This picture was taken before COVID. So this is really the first time all my students come together. We're able to present our work and eat together, right? So please check the program this year because I wasn't able to give you a detail of our model, but reading the paper, attending my student presentation, you're able to interact with my student and then chat with them on the hallway. And that concludes my talk. Thank you.
Okay, so I think we have plenty of time for Q&A. So if you have a question, please come to the mic and say your name and affiliation.
Hi, I'm Sam. I'm from the National Renewable Energy Lab. My question's about how you would apply a system like this to simulations that are intensive, but maybe the visual representations are more simple.
So can you say one more? You said, how do I apply the surrogate to
a simulation that's complex? So you would want a system like this, but the visual representation is less complex. So maybe it's not a volume; it's a 2D graph of some kind.
Right. Yeah. Yes. I think the thing is, a lot of time, the behind the scene, the data is so complex, but the output is not this, right? Like a bar chart or a scalar plots, right? Our focus has been on scientific visualization. So we are actually automatic generation of, simpler visualization like bar chart, scalar plot. I know there's more than that. I think it's actually a pretty interesting idea because this requires automatic visualization design for data without using human intervention, right? So this is actually another subgroup my students are looking at. But I think we haven't done anything, but I would imagine, just think about it. Can you just supply a lot of bar charts and then you will understand this bar chart and I can train and I can predict, but we haven't tried, but this is a really interesting idea.
Yeah, and my follow-up to that is, how do you think it would impact the runtime or the computational costs of training this kind of system? Is it dependent on the complexity of the visualization that you're training on?
I think in this case, right, most likely the complexity is not coming from the visualization, it's going to come from the simulations. Like for example, right, our surrogate, the goal is actually to bypass the simulation. A lot of times the visualization itself is fast, but it's the data generation component slow. And our surrogate is exactly bypass that. Right? So I would think that most of the complexity will come from most of the complexity reduction will come from the simulation, not from the visualization.
Hi, Lars Sinsen. Anyway, hi, Lars Sinsen, University of Münster, Germany. Thank you, Anwei, for this nice talk. I have one question about your graph neural networks that you're generating. So you decided to do like a cell-centered based approach to build your graph. Why is that better than going with the adaptive grid that you actually have?
Yeah, so you're asking like the trade-off between cell center and other like a node center approach?
Yeah. Yes, exactly. Why is the cell-centered better than the node-centered? Why do you go for that?
I guess this is, I think, obviously we haven't tried, maybe as Nick can say, we haven't tried node center, but my understanding is that maybe it's wrong. It's like the impact ocean, when you actually tessellate from the side, right, the cell created is actually a Voronoi cell. So actually the data produced is actually the cell center. That's my understanding. Right, but maybe that I think what coming from it is that the construction of graph need to consider how the original mesh was produced. If the mesh was cell center mesh, then you do that way. But if you know that the mesh is node center, such as from a parametric grid, you need to adopt. We haven't tried that, but I think that's something that we should try and compare, and maybe apply to a different simulation to see whether that will make any difference.
Okay, thank you.
Thank you.
So we have a question from online. So it's from Stephen Zellman. So the question is, would it fundamentally be possible to move the camera into the volumetric solid gate? It looks as though the network was trained using an orbiting camera.
So is it possible to
move the camera into the volume?
Oh, okay. I think so far we have not done that, because I think the one difficulty is moving into the volume. All of a sudden you have a much less constrained space, but the thing is because our neural network is to model based on training data, right? So if you are able to associate, for example, you do polar representation, you are able to associate the radius, the angle with each images. I don't see why not, but I can imagine your training data size is going to be a whole lot bigger, right? And then the result is that the training time will become bigger. But I think it's possible. But the cost we haven't investigated. I don't know how much longer the neural network is going to become.
So another question from online, Marco Egos. So his question is about generalization. How are the models depending on the data used for training?
Okay. Now, I would say, for example, the surrogate, GN surrogate, in situ surrogate, and UDL is very much dependent on simulation data. Meaning, I don't believe that our model can be used for unknown simulation input arbitrary parameters. So it's very data dependent. Now, so I would say for now, for all the work I present, because I think about the particle autoencoder also depends on the geometry of local neighborhood, right? So now, if your training data, again, the same thing, if the training data captures sufficient variation of local neighborhood particle, then we can apply to different data, right? But if the data has very different characteristics in terms of local distribution of the space and also the value, then again, so that will say this is actually the limitation of neural network, and then you need to go back to work on your training data to make sure you cover the things. For the important-driven latent representation, we actually, remember what I discussed was that it depends on the spatial range, which means actually we are not actually particularly focused on the definition importance. We focus on where the important regions are. So actually when we're training, we try to do a random sampling of different regions, different size, and assuming they are the important, we try to use that to train the autoencoder. So in that case, I think it will be a little bit easier to extend to a different data set because we actually not assuming any kind of importance. We try all the regions and then to generate latent. So that part is probably a little more less dependent. But I would say simulation surrogate definitely is simulation specific.
So another question from online, Chasa asked, well, so the question is, since uncertainty visualization is becoming increasingly important, is there a possibility to learn uncertainty across ensemble members with surrogate models or machine learning?
Yeah, so this is actually our incoming project. So that's our next project. We have a new project actually led by Christy Potter. We try to understand the uncertainty of the model. So I think this is, I would say this is the most important piece of work. So far, we're able to say, give me a parameter, I give you a result, right? But the goal is to run a series of parameters. How do we characterize the uncertainty? How do we characterize the sensitivity? Is something we have not done sufficient, but hopefully in the next 2 to 3 years, we are going to come up with something to do, led by Christy.
So another online question, Soma Dutta. So his question is how expensive it will be to use a model for inferencing data feature in situ for unknown simulation cases and do it in a distributed setting.
Right. I think I heard it's unknown, right? Distributed setting. Like I said earlier, right? So for unknown simulation, we don't have the confidence yet. We are able to predict it's in unknown simulation, but distributed manner, I believe that it will help tremendously because, like I say, right, I think this community, LDAV, need to focus on is how do we bring down the cost of training, but distributed computing always certainly help. Right. I don't know whether that answers the question.
Okay, so actually I have a follow-up question. So like the first 3 words you present is really related to with like ensemble or simulation parameters. So you also give a case where you have 32 different parameters. So those parameters are typically, right, they're pretty kind of uncertain, or you can say they're certainly non-linear relationships. So my question is, so how would the machine learning work you have done can really help the scientist to kind of cover the kind of like, or maybe sample the parameter space to better really understand the relationship between the simulation parameters and the output. So to deal with this, right? So actually in 2019 we have a paper. Actually, that's a best paper on mentioning. So what we do is how can you reproduce or how can you predict uncertainty such that we know certain parameter value is not as sensitive. So what we do is like we use dropout. So essentially, every iteration, we take the 10% out of the neuron, out of the neural network to train, and then in the inference time, also the same thing. We take the 10% of the neuron, run simulation, get a result, take another 10%, so randomly sample 10%, and we actually collect a series of the result. Now, different parameter is going to have a different sensitivity into the loss of a neuron, and from there, we can just evaluate the sensitivity of the parameter with respect to the model. So now that's just one example. So to inject uncertainty to the neural network to see what is going to happen in the output. And that's one way we try to collect sensitivity and uncertainty, and I believe there are other ways that we can try. Right. So any other question from the audience here? So maybe another one from me. So a lot of work you have done are based on the CNN granular net. So have your team start to work on something related to with implicit neural representation, like coordinate-based network, which simply use MLP, right, to really take the input coordinate. They can predict any value of interest. So how that would compare to the existing what you have done, or maybe there's an improved version that's coming out of that.
Yeah, I guess that we are working on it. Okay. So the implicit, like a nerve-based neural network, implicit neural network has a lot of potential for rendering, and actually we are also working on can we use that for simulation surrogate. We haven't have any result yet, but hopefully coming. But Charlie, that's really a hot topic right now. Yeah.
Okay, so it's no more question. Let's thank Professor Sun one more time for his great talks.
Thank you very much.
Okay, so while going to the coffee break, the next session will be starting 10:45. Okay.